Hi, I'm Dane Quinn from the University of Akron. Today's video lecture, we're going to talk about parallel gear trains. We can mesh gears together in a parallel gear train. So as seen here in the figure, we have two gears that are in contact, and we'll define the angular velocity of gear 2 as omega 2k, and for gear 4, we'll have omega 4k. And as we saw in the previous lecture, we can identify the gear ratio, right, which is omega 4 divided by omega 2, as the ratio of the number of teeth, so minus n2 over n4. I'll point out again that angular speeds and these are the omegas, right? So omega 1 or omega 2 is defined positive in the plus k direction, so counterclockwise. As a result, the change in direction between these gears, so the fact that if omega 2 rotates counterclockwise, then omega 4 would rotate clockwise. So this is included in the speed ratio through the negative sign, right? So here, if omega 2 is positive, omega 4 is negative, or vice versa. I define each angular speed as positive in the counterclockwise direction, and then I let this change in direction be taken care of in the constitutive law, as opposed to defining omega 4 as in the minus k direction, positive. We'll see an advantage of this next. Multiple gears can be meshed together in what's known as a simple gear train, right? So again, N2 is connected to N3, which is connected to N4. So again, if the angular velocity is defined as positive counterclockwise for all three gears, then omega 4 divided by omega 2, well, we'll just look at pairs of gears. Omega 4 divided by omega 3, right? So we'll look at gear 4 and 3 in contact, and then we'll look at gear 3 and 2 in contact, keeping in mind, of course, that these omega 3s will eventually cancel out, right? But when I do it this way, 4 and 3, well, that's minus n3 divided by n4. 3 and 2, minus n2 divided by n3. Right? So that's the speed ratio, the gear ratio for 4 and 3. This is the gear ratio for 3 and 2. Well, the number of teeth on gear 3 cancels out, and I am left with n2 divided by n4. Note, however, that this is actually different than the previous example. If I have just two gears in mesh, I have a change in direction between the two. But by introducing this third gear in the middle, the gear ratio actually stays the same, right? So that's the absolute value here. But this now becomes positive, indicating there's no change in direction between omega 2 and omega 4. They actually rotate in the same direction. So N3, or gear 3, does not change the overall ratio Right? So if you just looked at the absolute value, it's the same for both cases, but changes the direction of the output. This is known as an idler gear. Again, it doesn't change the overall speed ratio, but does change the direction of rotation from the input to the output. These are very common. It's what's in your car transmission. As you put your car into reverse, the direction of rotation for the engine, that stays the same. But by introducing an idler gear within the transmission, you can reverse the orientation of rotation of the wheels, right? So particularly the output. By introducing that gear, you can go from forward drive to reverse. Now, we can have more complicated gear systems, such as those described by a compound gear train. And that's a system in which one of the axes has multiple gears. So looking at this, right, we have gear 2 is in mesh with gear 3, but then gear 3 and gear 4 are actually rigidly connected. Then gear 4 is connected to gear 5. I've kind of given a side view down below, right? So this would be in 2. This would be in 3, and again, that's going to be rigidly connected to N4, which then drives N5. So once again, defining all of these directions as omega 2, this will be omega 3. I'm going to go ahead and define omega 4 as well, even though they're the same. Omega 5 is then defined like so. If I want the gear ratio for this train, it's omega 5 divided by omega 2. Well, just like we did before, omega 5 divided by omega 4, let's look at these gears in pairs. All right, so 4 and 3, and then 3 and 2. So when I do this, each one of these gear pairs has a relatively simple relationship. Gear 4 and 5, well, that's going to be minus N4 divided by N5. Notice that 4 and 3 is simply 1 because they're rigidly connected. These two gears have to rotate with the same angular velocity. And then finally, 2 and 3 minus N2 divided by N3. So putting this all together, we see that this is plus N2 times N4 divided by N3 times N5. And this becomes the overall gear ratio. So now, how do we calculate these? Well, really, if we're given the number of teeth, then we can immediately determine the gear ratio. Right, so let's look at an example. Imagine that N2 is equal to 24. Let's take N3 to be 15. N4, let that be 40. And N5 is equal to 12. Right, so as a result, we can calculate this gear ratio according to this formula as, well, 24 times 40 divided by 15 times 12, which ends up being 16/3, or 3 1/3. Now, I will notice that the number of teeth has to be an integer. You can't have half a tooth. As a result, this gear ratio has to be a rational number. Rational numbers, remember, are ratios of integers, right? So whatever's up here in the numerator has to be a integer, right? N2 times N4. N3 times N5 also has to be an integer. So only rational speed ratios are possible. So you could not, for example, have a speed ratio of pi, right? Pi is an irrational number. You couldn't have a speed ratio of square root of 2. That's an irrational number. Now, I can have a speed ratio of 1/7, but it has to be expressed as the ratio of integers, or a rational number. So this kind of complicates the design of gear trains, right? So again, here, this is the gear ratio that we were looking at before, right? So that's going to be omega 5 divided by omega 2 is N2 N4 divided by N3 times N5. So again, any gear ratio must be rational. So here, I can write it as an integer p divided by an integer q. So the consequence of this is that the numerator, which in this case is N2 times N4, must have a factor of p. Likewise, the denominator and that's going to be N3 times N5 in this case, must have a factor of q. And the remaining factors of the numerator and the denominator must cancel out. Because after all, I can't have a fractional number of teeth. So let's kind of see how that works out. Well, in this, I'd like to design this gear train so that we obtain a gear ratio of, say, 9/2. All right, fine. That means that omega 5 divided by omega 2 has to be 9/2. Well, we can factor both the numerator and the denominator. In this case, factoring the numerator is 3 times 3. Factoring the denominator is 2. And that has to be equal to N2 times N4 divided by N3 times N5. So here, that means 2 times 4, N2 times N4. It has to have factors of 3 with multiplicity 2. And N3 and N5, that product has to contain a factor of 2. So how do we ensure this? Well, at this point, it's kind of an art form. There are lots of different solutions for choosing N2, N4, N3, and N5 to work out in this way. So one thing that we can do is let N2 have one of these factors of 3, right? So it's going to be 3 times, some number. And this is something that I'll choose in a minute. N3, well, I'm going to let that have the factor of 2, right? So it's 2 times, some number. And again, x, v to be chosen later. N4 is going to have the other factor of 3. And N5 is going to be chosen later. As a result, N2 times N4 divided by N3 times N5, so this is the speed ratio that I'm looking for, is 3 times x times 3 times y divided by 2 times v times w. So again, these things are all left to be chosen, but what I know is that if the overall speed ratio is 9/2, then x times y has to be equal to v times w, right? So that these cancel out. And this is not to say that x has to be equal to v or y has to be equal to w, right? But their products have to cancel out. So now, again, there's a lot of ambiguity here, right? We can choose these things in lots of different ways. N5 is equal to W, right? So let's say that, well, in this case, W is the number of teeth on gear 5, right? So let W be equal to 15, right? Which is actually equal to 5 times 3. And here, V is related to the number of teeth on gear 3, right? So let's say that N3 is 24, which means that V is 12, which is equal to 2 times 2 times 3. See, there's a lot of prime factorizations that kind of go on here. As a result, now I need to choose x and y so that their product is equal to v times w. Well, really, I'm just going to take these different factors and distribute them between x and y. There's, again, lots of ways of doing this. So one way of doing this is to let x be equal to 5 times 2 times 2. So I'll take that factor of 5 and those two, right, which ends up being 20. And y gets then the remaining factors. So that's 3 times 3, which of course is equal to 9. As a result, right, we've designed our gear train, and N2 is 3 times 20, so that's 60 teeth. N3 here is 2 times 12, so 24. N4 ends up as 27. And in 5, then again, is just V or W, which is 15. So here's one solution for this design. There are lots of other solutions, but again, kind of thinking about the different factors of the gear ratio and the number of teeth will help you to ensure that you have an integer number of teeth on each gear. So that's a quick introduction to parallel gear trains. And thanks so much. I will talk to you again. Bye.